But what the law of large number is trying to talk about, what it's emphasizing, is if I take a sufficiently large sample, then my sample mean will converge to the population mean. So which in general, what it's trying to say, statistic converge to the parameter, to the true value of parameter when the sample size is sufficiently large. Now the bottom line is the more sample I take, the more I'm very close to the truth. I'm going to say that again. The more sample I take, the more I'm very close to the truth. And that is why this is called the law of large numbers. Large numbers in relation to the sample size that you're going to choose. If you take a look at the interpretation now, the larger the sample, the better the sample mean approximates the population mean. You know, we all acknowledge the fact that model is not the same as reality. We use model to depict reality. There's always going to be a gap. The same way there's going to be a gap between sample mean and population mean. But the law of large number emphasizes choosing the large sample if we really want to close the gap. We're not going to totally close the gap. We're only going to bridge the gap. We're going to make it closer. And that's what I mean by convergence. Now, I'm going to walk you through this example right now. Okay. We have let X be equal to the numbers of hours an American watches TV on average day, and suppose it is known that X has a mean of 3 and a standard deviation of 2.25. Okay, I wanted to take notes of that. Now, if you take a look at the statement here, that statement is for the population because you were not told about the numbers of Americans that it took for them to have a mean of 3 and for them to have a standard deviation of 2.25. We're actually going to refer to that mean as 3 to be population mean. We're also going to refer to the standard deviation here as the population standard deviation. Of course, we all know from one sample to the other, we expect the numbers of hours they watch TV to varies. And for us to be able to have the understanding of the probability distribution of the random variable under investigation, they gave us this. They gave us this. Now that is giving us a picture that time spent watching TV, okay, the probability distribution is not normal, it's skewed. Okay, so this is skewed population. But you know what? We have a skewed population now. They gave you the mean, they gave you the standard deviation. And the question asks about, take a sample of 10 Americans, which means sample size equal to 10. What are the mean and the standard deviation of the sampling distribution? Now, I need you to pay attention now. Okay, I need you to pay attention. Theoretically, the mean of the sampling distribution is always going to be equal to the population mean. The population mean was given initially to be 3. Whatever is the value of the population mean, then the mean of the sampling distribution will always going to be that. Is there any question on that? The mu subscript X bar is the mean of the sampling distribution. Mu without subscript X bar is the population mean. The population mean has already been given to be 3, so automatically Okay, the mean of the sampling distribution is going to be equal to that. But you know what? We want to figure this guy out. The sigma x bar. What is the difference between the sigma x bar and the sigma? Now I want you to pay attention now. The sigma is just talking about the population standard deviation. That is the sigma. Population standard deviation. But sigma x bar is a standard error. There's a difference between the sigma x bar and the sigma. You know, some questions that I received, and I want to appreciate those of you that visited my office hour yesterday. Now, some of the feedback that I got, student has a question about in real life, when we are conducting experiments, do we go into population so many times? Because the sampling distribution preaches that. The sampling distribution, and my response is going to be, we don't go into population so many times. We only go into population once to choose whatever sample we want to choose. But what is sampling distribution talking about? I needed to listen now. The sampling distribution will actually give us an opportunity to see if I go into population so many times and I choose a sample and I compute statistic, the statistic will vary. I'm going to say that again. The distribution gives us an opportunity to see how statistic, maybe I'm talking about means, or I'm talking about standard deviation, how they varies, or I'm talking about proportion, how they varies from sample to sample. And if we understand how they vary, of course, then we can look at the variation, which means if I have I have samples, I have so many sample means. Okay, if 300 investigators should go into the population, they choose the same sample size, they're working on the same goal, they're actually going to have different value for means. And that's why at times you see on the news that they report different value, despite the fact they're working on the same goal. The sampling distribution enable us to see the possible values the statistic can take. Now, when we know the possible value statistic can take, since means now vary, we can find the mean of the means. We can find the standard deviation of the means. I'm going to say that again. Mean varies. Okay. We can find the mean of the means, which is the average of the averages. We can also find the standard deviation of the averages. The standard deviation of the averages is what we call standard error. Standard deviation of the averages is what we call standard error. With the sampling distribution that we did, we're able to arrive at a formula. Okay, if you take a look at this particular formula now, if you go into population once, because like I said, you are not going to go into population more than one time. We go once and take our sample once. But the idea of sampling distribution has given us a formula that we're going to use for standard error, so that we don't necessarily go into the population more than one time. And and that formula is sigma over root n. And if you see the standard deviation and the standard error, they're only going to be equal if sample size equal to 1. It's not going to happen in research. We don't investigate one person. We investigate more than one person. And the moment the sample size is greater than 1, the standard error will be less than the standard deviation. Our intention is for the standard error to be less than the standard deviation. And when you take a look at that relationship right now, for 10 Americans, we actually got a standard error of 0.71. Of course, you know 0.71 is less than 2.25. The standard error here is less than the standard deviation. If I increase that to 100 Americans, I need you to pay attention now. Please pay attention now. I'm seeing a lot of exam 1 question here. So please pay attention. Now, irrespective of the sample size, whether sample size go up or not, the mean is always going to be equal. Whether the sample size is 10 or the sample size is 100 or the sample size is whatever, this mean of the sampling distribution will always be equal to the population mean. That is by theory, as you can see in both sides. But what is the difference? The difference between taking 10 samples and taking 100 samples, you can actually see that effect in the standard error. Now, I needed to pay attention to this guy right now. The standard error for 10 American is actually 0.71, but the standard error for 100 Americans is actually 0.225. Of course, the 0.225, the one for 100 is very smaller. If we compare 0.225 to 0.71. And I told you the other time that as sample size is increasing, the standard error will be going down. When the standard error is going down, that is the beauty of the research. More reliability. Does that make sense? Okay. Now, and that was why I made a statement here. And I said, X bar is less variable when we only have, okay, when we only have, you know, the X bar is less variable than when we only have n equal to 10, which means right now we have, you know, for n equal to 100, the standard error is smaller. When the standard error is smaller, what that means is that the several means that we have, okay, they are not far from each other. But if the standard error is huge, then the several means that you have, they have high degree of disparity. We don't want high degree of disparity. High degree of disparity is, you know, can be translated into disagreement. Does that make sense? And that's what we mean. But you know, some of you will now want to say, what would be the reasonable sample size? If I, as a researcher, I want to go into population, I want to conduct a study, whether it's going to be a social study or it's going to be economy study or it's going to be medical or whatever, I actually need the number of participants. How do I arrive at a particular number of participants? Then I'm going to say this. Using this particular formula here, like I said, that formula was derived using the idea of sampling distribution. That formula is the major takeaway from sampling distribution. That formula will save us unnecessary time going into population so many times. Don't forget, we only go one time. But this formula here that we got is actually giving us a sense as if we have gone more than one time. Okay, now if I really want to decide on the number of participants that I need for my study, then I need to be able to tell the world what is the standard deviation I want to tolerate and what is the standard error I want to tolerate. So those are the factors that determine sample size. A researcher don't just decide on the sample size arbitrarily. We don't do that. Now, take a look at this question. How large of a sample will we need in order to obtain an estimate X bar with a standard deviation less than or equal to 0.05? You need to have that in mind. Okay, if I want to have a mathematical interpretation for that right now, based on this study, okay, I want my standard deviation to be 2.25, that I want it to be less or equal to 0.05 within the standard error of 0.05. All what I just got to do is to solve the equation. I remember when you are in high school, you see yourself solving equation. My daughter used to ask me question when she got home, is going to say, why am I looking for X? I said, daughter, you're going to know why you're looking for X when you get to college. Now, this is college now. You know what I'm looking for? Yeah, I'm looking for the sample size. There's no way I will be able to get a sample size without solving equation here because I already have I have a standard error equation has something to do with the sample size. When I plug that in and I solve for n, this guy is trying to say, you know what? If you really want to achieve an error, a standard error within 0.05, then your sample size has to be huge. When your standard error is large, your sample size will be small. When your standard error is very, very small, your sample size will be large. And the takeaway here is that, the two of them has inverse relationship. Okay? When one goes up, the other one comes down. Okay. Now, you know what I want to do now? I actually want you to see what is behind the scene. I want you to see how the idea of sampling distribution was used for them to be able to arrive at the formula for standard error that we now use in a modern day world. Okay, I wanted to see the connection. Let's say we want to run a sampling distribution where we're going to go into population so many times. When I go into population so many times and I go once, how do I really know that if I go once, it's going to give me the same result when I go so many times? Let me tell you this, in statistics, in science, in general, there is nothing like authoritarianism. When you tell us something in science, you got to show us with the evidence. We got a statistical evidence. You got to prove beyond every reasonable doubt. Because of that, I'm actually going to go into this example right now, and I need you to pay attention. For instance, let's say I have a population of 4 research students. Okay? Now, let's say these are my 4 research students, ABCD, as you can see in the picture. And because all of them, I'm defining that as a population size. Whenever we want to talk about sample, we use a lowercase n. When we want to talk about population size, we use an uppercase n. Does that make sense? That's why you say an uppercase n equal to 4. Now, maybe the random variable of the interest is, I want to talk about their age. Okay, the age of the first, so the values of x is, age, the random variable x is the age in years. Okay, one of them is 18, the other one is 20, the other one is 22, and the other one is 24. Now, let us act as if, you know what I want to demonstrate right now? I actually want to demonstrate this. I want to demonstrate, give me 1 second. Okay, I want to demonstrate this guy here. I want to demonstrate that always population mean is the same as the mean of the sampling distribution. Okay, I want to demonstrate right now that population mean is going to be the same as the mean of the sampling distribution. And I need you to follow. Now, and let's say I find the average. Why am I dividing by uppercase n? I'm dividing by uppercase n because I'm using everybody. I'm using everybody. That's why I'm divided by uppercase n. My population mean here is 21. Now, I want to find the standard deviation. Why am I dividing by uppercase n? Is because I'm using everybody. Because if I want to get a sample standard deviation, I will divide by n minus 1. You remember? But right now, divided by n because I'm using all the data set. Now, what do you see? 21 is the population mean age of my research students. 2.236 is a population standard deviation. Okay, I got my mu, I got my sigma. And not only that, I want to look at the distribution of my data set right now, okay? Because I got 4 of them. The probability of choosing any one of them is going to be 1/4, which is 0.25, right? They're all going to have the same bar. When they have the same bar, that will be uniform, right? That will be uniform distribution. So which means the data set that I'm working with, when you look at the distribution of the population now, okay, it's actually uniform. It's not normal. Now you now know what I want to do now. And I want to demonstrate to the world that the same value that I got as the population mean, okay, the same value that I got as a population mean, which is 21, when I conduct a sampling distribution, I'm actually going to get the same. And I need you to pay attention. Now take a look at this. Let's say I don't have time. I now just want to choose a sample size of 2. Look at that. You see, whenever you see a lowercase n, I'm referring to sample size. So if out of 4, I don't have time to study all the 4, and I say, okay, can I just choose 2? If I choose 2 by sampling distribution, I need to be able to consider possible outcome. What I'm going to do, I can write in the column 18 to 18, 20, 22, 24. In the row, I'm actually going to write that. Then I'm going to be looking at the combination. If you take a look at what I have right now, okay, what I have right now is when is a possible choose. I'm actually going to have, because don't forget, I'm sampling with replacements. Maybe I close my eyes, I pick on somebody, and that person is age 18. I replace the person back, and I go back again randomly. There's possibility I'm going to choose that person again. That's where you see 18, 18. Does that make sense? So what you see here is a possible possible samples you can have. And what is the possibility? 16. We got 16 possible ways of choosing 2. And let me tell you this. If I have 16 researchers to go into that population of 4 students and choose 2, this is their possibility. They're going to have different results like this. That's what we mean. Now, what are we going to do now? We're now going to find the mean for each sample. 18 plus 18 divided by 2. 18 plus 20, 20 divided by 2. When you find the means right now, you actually going to have the one here as a mean. How many means do you have? 16 sample means. 16 sample means here is more or less like I have 16 researchers, 16 investigators. They go into the population. They choose 2, and they have 16 different values. Now, when I have this guy now, these are means, right now. These are means. If I want to find the mean of the sampling distribution, I'm going to say that again. If I want to find the mean of the sampling distribution, then I'm going to find the mean of the means. If I find the mean of the means, okay, if I actually find the means of the means, okay, I'm actually going to take a look at this. It's still going to give me the same 21. Don't forget the other time. When I find the population mean, it was 21. When I find the mean of the sampling distribution, it's also 21. And that was the reason why we will impose a theorem, and we said anywhere in the world, the mean of the sampling distribution is always going to be a population mean. We did not came up with that statement arbitrarily, because we've studied possibility, and at the end of the day, you can see that gives us 21, the same value that we got when we've calculated the population mean. Now, not only that, another thing that we saw was that when you take a look at this guy now, you're going to see that apart from the fact that the sampling distribution gives us opportunity to be able to see how statistic varies, how means varies. But do you know that sampling distribution is also going to tell us some values we agree, and that will bring in weight. Take a look at that. How many times? We have 19 twice. It means that is more or less looking like two investigators that have the same values. It's possible. If you look at 20, how many times 20 occur? 3 times. It's like out of 16, we got 3 investigators agree, that have the same value. Look at 21, look at 22. Because of that, do you know we can actually construct histogram based on that? If you take a look at 18 here, okay, the 18 that you see here that I plotted, 18 we mean how many times does 18 occur? 1 out of 16, 1 over 16. This is plotted against 1 over 16. How many times does 19 occur? 2. 2 out of 16 is the second bar. And it continues like that. Oh my God. Look at the graph right now. That is looking normal. But initially, we didn't start from normal. We started from uniform. Now, but you know what? I said something the other time. What has changed now? The distribution has changed to normality. And we realize that the mean of the sampling distribution and the population mean is the same. But can we investigate out of the standard deviation? Let's take a look at it. Now, initially, the population standard deviation was actually 2.236. This is the population standard deviation around the original scores in the population. But when we look at the standard deviation of the statistic, okay, take a look at this guy now. I want to find the standard deviation of the statistic. What is my random variable? The random variable is X bar. Look at that. X bar is a random variable, not X. Deviation around, that very mu is actually going to be the mean of the means. We now want to know the deviation. How far are the several means from the mean of the means? And by the time we find out, we got 1.58. Okay, we got 1.58. Now, what do you see? There is a difference between the standard deviation of the population that we got the other time, which actually was 2.236, and the standard deviation of the statistic. The standard deviation of the statistic here is what we call the standard error. When we now look at the mathematical, from the sampling distribution, we got this, and we want to do something. We know we're not going to go, we don't have resources to go into the population several times, because it is only when I go several times that I will be able to arrive at this. Now, if we don't want to go several times, we want to go once. Can we have a way to look at the mathematical relationship between 1.58, please listen, between 1.58 and 2.236? We now realize this. We realize, you can take your calculator right now. We realize that the standard error, we realize from this that the standard error is the same if you don't want to go into the population several times as preached by the sampling distribution. Or what you just need to do, oh my God, if I know the standard deviation, what I needed to do right now with your calculator, put 2.236 divided by square root of n, the square root of n, and see whether you're going to get it. Try that right now. What do you get? 2.236 divided by square root of n. Of course, you know your n. What do you get? Do you get 1.58? What do you get? Square root of n. I want somebody to confirm that before moving forward. 2.236 divided by square root of n. What do you have? Your n is 2. Plug in n to be 2. What do you have? I want somebody to confirm that. You said what? No, I said 2.23. This. Let me just go back. This is the standard deviation here is 2.236. So 2.236 divided by square root of 2. Do you have 1.58? Yeah, you get 1.58. And that is the reason why we know. That is how we know that we know the standard error is going to be standard deviation divided by square root of n. We don't necessarily, we are not going to do all this in a normal research. We don't go into population several times. But theoretically speaking, because we're able to see the formula, the sampling distribution enables us to get a formula that we can actually use. And that formula is the moment I know the standard deviation and I know the sample size, I can calculate my standard error. Because in statistical analysis, standard error is very, very crucial. Without standard error, there is no foundation for statistical inference. Without standard error, there is nothing. You can never test hypothesis. Very soon you're going to talk about hypothesis testing. Without standard error, no hypothesis testing. Without standard error, no confidence interval. So standard error is the key. And that is why you need to be able to know that. Now, in summary, this is for the population. Where n equal to 4. The population mean was 21. The population standard deviation is 2.236. The distribution is uniform. But after the sampling distribution, you see what happened? Where we take a sample size of 2, the mean we made the same. The mean of the sampling distribution is the same as the population mean, but the standard deviation, they're not going to be the same. The population standard deviation is 2.236, but this guy is the standard deviation of the statistic, which is called standard error. We expect standard error to be less than that. And if I want to get the standard error without going through sampling distribution, all what I'm just going to do is to actually have the standard deviation divided by the square root of the sample size. And I'm actually going to look at that. I also have that. Now, what is visible? When I go into population, I take a sample. Okay, I don't go into population so many times. We go one time. We choose a sample, then we find the sample mean. This is the formula that we use in finding the sample mean. What do you see? You see n, which is a lowercase n, which is the sample size. Then we compute the standard error. You see? If I want to compute the standard error now, okay, don't forget I said it is a ratio of standard deviation to the square root of the sample size. We're able to derive this formula using the idea of sampling distribution that encourages repeated sampling. Now, that was why I said this standard error is very, very crucial in statistical inference. It is a measure of variability in the mean. And not only that, I said a measure of variability in the mean from sample to sample, it's also a measure of precision. Okay. And if you look at the relationship between the sample size and the standard error now, the sample size is occupying the denominator position, which means the standard error and the sample size are inversely related. They move in different directions. When sample size increases, standard error goes down. Our intention in statistics is to have a standard error goes down. But you cannot eat your cake and have it. If you want to have a standard error goes down, then you need to increase your sample size. Does that make sense? But why are we not using the entire element in the population in the first place? Because when we are conducting research, even though we're looking for efficiency, we are also limited by budget. What about the cost? Now, which means, I told you, the mean of the sampling distribution is always going to be equal to population mean. Now, if I have a normal population with this, where mu is the center, then for normal sampling distribution, then the mu subscript x bar is going to be the center. But let me tell you this. The sampling distribution curve compared to the curve for the original variable, the one for the sampling distribution is actually going to shrink in. Why for the original data is going to spread out, even though if the two of them follow normal. When something shrink in, okay, it's shrinking because you've used a large sample. The one that spread out, maybe you use a smaller sample, and that's what I'm demonstrating here. Take a look at that. The blue one is spread out because maybe you are using smaller sample, and when it's spread out, that's not good. When it's shrinking, then maybe you are using a large sample size. When it's shrinking, the standard error is going to be small. When it's spread out, it's actually not going to be. Okay. Now, these two. Now, what if in a situation where I'm not talking about normal? Here, I'm still talking about normal. There's possibility a population may be normal. Now, I need you to pay attention. When population distribution is normal, whatever sample size you choose, whether small or large, sampling distribution will be normal. I'm going to say that again. When the population is already normal, whatever sample size you choose, whether small or big, the sampling distribution will also be normal. Does that make sense? But the only difference between two normal is just this, which depends on the sample size. When the sample size is large, it's going to shrink in. When the sample size is small, it's going to spread out. Now, what if in a situation where the distribution is not normal? I need you to pay attention now. You are working with a distribution of data set is not normal, just like the one we did the other time on uniform. That's not normal. Okay, then we need to apply central limit theorem. Statistics is like a story. Now, what does central limit theorem says? The central limit theorem said if the population that you are choosing from is not normal, if you want to guarantee sampling distribution to be normal, take a sufficiently large sample. And now large is a large. It has to be at least 30. Does that make sense? That's what we mean by central limit theorem. Central limit theorem says that if the population you are choosing your data from is not normal, if you want your sampling distribution to be normal, then choose a sufficiently large sample. And now large is a large. The minimum requirement is at least 30. Okay. Whether norm, and that was why I said, even if the population is not normal, sample mean from the population will be approximately normal as long as the sample size is large enough. And now large is a large. It has to be at least 30. Okay. And the property still applies. The one that apply to the normal population also apply to that. Now, let us have that in comparison. Oh my God. Look at the blue one. The blue one is trying to give you a picture of a distribution that is not normal. And the red one is trying to say, okay, you know what? Irregardless of the distribution of your population, if your sample size is large, if it is large enough, the distribution is going to convert to normality. Now, this is what central limit theorem is talking about. Now, let me tell you the difference between them. Law of large number, central limit theorem. Law of large number focuses on convergence of statistic to the parameter. I'm going to say that again. Law of large number emphasizes when sample is sufficiently large, the sample statistic converges to the population parameter. But what about central limit theorem? Central limit theorem does not talk about convergence of statistic to population parameter. But do you know what central limit talk about? Central limit talk about the convergence of the probability distribution. It's trying to say when the sample size is large, even though you don't start with normal, you're going to end up with normal. I don't know whether you get that. So the two are not saying the same thing. Okay, now take a look at this now. If the population distribution is skewed, just like this guy, okay, now it it will become normal eventually if the sample size increases. That is what we mean here. Here I'm superimposing. I have two curves. One is not, one is skewed, but the other one is actually with last sample, it become, normal. That's what I mean. And let me tell you this. What is the significance of having a distribution of statistic to be normal? The significance is this. That will enable us to conduct statistical inference with the statistic. It's going to make probability computation easy. And that's why we celebrate when the distribution becomes normal. Okay? Now, I'm going to walk you through an example. Suppose a large population has a mean of 8 and a standard deviation sigma equal to 3. Suppose a random sample of size n equal to 36 is selected. What is the probability that sample mean is between 7.8 and 8.2? I needed to pay attention. I'm seeing a lot of exam 1 question here. Pay attention. Focus on the board. Do you know what? If you take a look at this question, they did not tell us about the distribution of the original data, whether it's normal or not. We're not interested in that. But pay attention to the sample size. Because sample size has passed a threshold of central limit theorem that emphasize that how large is large, it should be at least 30. Then in this question, central limit theorem applies. Now, if I want to find out, then I need, because it is normal by central limit theorem, normality facilitates standardization. Statistics is like a story, a beautiful story, a thrilling story, a story that goes on and on and on. We don't just do what we do. We got to reason why we do what we do. Now, right now, because the sample size is large enough, we can apply central limit theorem. Normality applies. And when normality applies, normality facilitates standardization, the use of z-score. Now, what am I going to do? I know my mean to be 8. Then I calculate the standard error. And after calculating the standard error, the z-score that I'm actually going to use, it would be different from the z-score you used before. The z-score you used before was targeting individual x, where you have x minus mu over standard deviation. But the z-score right now is going to center on the mean. It's going to be sample mean minus the population mean divided by the standard error, which is what you have here. Take a look at this. I want to standardize 7.8. You see what I have? Standardizing. You see the denominator. The denominator is standard error, which is what the standard deviation divided by the square root of n. Now I also standardize 8.2, and at the end of the day, after standardizing, I got the probability of z between negative 0.5 and 0.5. What am I going to do when I get into R? That is just going to be p norm of 0.5 minus p norm of negative 0.5, and the final answer is actually going to be that guy. It's going to be 0.3830. But let me tell you this. Without central limit theorem, there is no way we're actually going to use the idea of standardization. Normality facilitates standardization. And how do we get normality? When the central limit theorem applies. Now, what is the threshold? What is the requirement of central limit theorem? The sample size has to be at least 30. If it is not, central limit theorem will not apply. If central limit theorem don't apply, then that will not facilitate the use of z-score. The use of z-score simplify the whole thing. It will make the probability around that very easy. Oh my God, this statistical party is over. So make sure you all stay safe and have a lovely day. Bye for now, everyone. Yeah, you can come with your question. Yeah. Okay, go ahead.